Welcome to Virtual Science. Today we're starting a new unit on states of matter, and so we'll be talking about how matter changes from solid, liquid, gas, plasma. Before we do that, we need to understand a little bit about how matter moves and what's happening with the particles in the matter, not just that it changes state from solid, liquid to gas. So the explanation of how the particles in matter behave is called the kinetic theory. And you probably heard the word kinetic before from elementary school. It means energy in motion. So this really is going to describe how the particles in matter are moving and how they behave based on how they move. So there's three parts to the kinetic theory. The first part is that all matter is composed of tiny particles. Now, in the last unit, we realized that the particles were all elements or compounds. And the elements or compounds could be pure or they could be in mixtures. Most of the time they're in mixtures. There's many more mixtures than there are elements. Okay? These tiny particles are in constant motion. So they're moving around. They're not static. Because they're constantly moving around, the atoms or particles collide with each other and their container. So, if you think of something like the top of your desk or the walls, the little particles are moving around in there. And then if they're in something like, the gas particles inside of a basketball, those gas particles are bumping into the side of the basketball. Now, number 2 and 3, this is going to come up a number of times this year. This is a lot of times a source of confusion for 8th graders. Okay, and that is the difference between temperature and thermal energy. Put in your notes here that thermal energy is the total energy, kinetic and potential of the material's particles. So if we add up all the energy of those moving particles in something, then the thermal energy is the amount of energy that's in the total. So the amount of thermal energy in something really depends on how much of the substance we have. So for example, if we went down to the ocean and we stuck a cup of water, got a cup of water of the ocean, and the ocean and the water in the glass were the same temperature, because we just dipped it in the ocean, well, the thermal energy in the ocean would be much greater than the thermal energy of just a glass of water that we had scooped out, even though they would have the same temperature. Because thermal energy is the total energy of the particles. It depends on how many particles there are. So if you think about the number of water molecules in the glass versus the number of water molecules in the ocean, there's a lot more particles in the ocean. Now, like we said, the temperature is the average kinetic energy of the particles in a substance or how fast they're moving around. So if we continue with that example where we had the glass of water, we had the whole ocean, we're going to have the same average kinetic energy. The particles in the glass of water are moving around just as fast as the one in the ocean, so they would have the same temperature. But as I just said, the total energy of the ocean would be much greater. Now, suppose we took that glass of water and we heated it, and we got it to where it was ready to boil. The average energy of the particles in the glass would be much greater than the average energy in the ocean. So that we would say the temperature of the water that we heated was higher. But still, when we talk about the total thermal energy of the ocean is still much greater than that glass of water that's almost ready to boil. And if you think about how many particles there are in the ocean, there's just a tremendous amount of particles in the ocean. So another way to think about it is if you had that glass of water and it was ready to boil and you dumped it in the ocean, would it really change the temperature of the ocean? Would it have those particles have enough energy to really make a difference when they got mixed into the ocean. And of course, it's silly. Like if you went to the beach and you were like mom or dad or whoever you were with, the ocean is kind of cold, and I wish the water was a little warmer. And they were like, yeah, well, let's, we'll just heat up a couple of glasses of water and dump it in there. It's not really going to change the total of the ocean very much because there are so many particles. And if you think about the sun beating down on the surface of the ocean all day long and the ocean absorbing all that energy from the sun, the total energy stored in the ocean is tremendous because of how many particles there are. Okay? So temperature does not depend on how many particles there are. So as we said initially, when we went down there and got that glass of water and stuck it in the ocean, it would be the same temperature as the ocean, and it wouldn't matter how many particles there were. Where thermal energy depends on the total. Another way you can think of the difference between thermal energy and temperature is the old saying, like a watch pot never boils. So if you put 2 pans of water on the stove, and they both just came out of the faucet, so they started off the same temperature. And one of them was just a small pan of water. And the other one you had in a big kettle, like a couple of gallons of water in there. And you turn them on, put them on the burners, and you turn the burners on hot. And both of the burners let out the same amount of heat. Well, the one where you have the huge amount of water in the kettle is going to take a lot longer to gain enough total thermal energy to reach boiling, whereas the small amount is going to take a much smaller total of energy to be transferred from the stove into the water to get it to boil. Now, the lower the temperature, the slower the particles move. When you raise the temperature, the particles move faster and faster. So that's one of the key things that we're discussing. So there's a short video I wanted to share with you on the difference between thermal energy and temperature.
And temperature. Let's start by comparing 1 cup of coffee to 2 cups of coffee. What doubled, temperature or thermal energy? Remember.
Okay, now think about the question there. If you have 2 cups of coffee and they're both at the same temperature, the temperature didn't double. But because there's more coffee, then the amount of thermal energy or the heat stored in the coffee.
Temperature measures the average kinetic energy. 2 cups of coffee will not have double the temperature of 1 cup of coffee. But 2 cups will have double the thermal energy than 1 cup because the mass or size has doubled. Now what about the 1 cup of coffee versus the iceberg? The iceberg is several thousand times larger than the cup of coffee. Even though the iceberg...
So he just showed us that the iceberg is 10,000 times larger than the cup of coffee. So there's 10,000 as many water molecules in the iceberg as there is in this cup of coffee. So because there are so many molecules, and all of the molecules, even though the iceberg is cold, even though it's freezing, they're still moving around. So the total energy of 10,000 as many molecules is still greater than the cup of coffee. Now, the iceberg is at a lower temperature, the coffee is at a higher temperature, so the average of the coffee is higher than the average of the iceberg, but the total energy in the iceberg is still greater. The total energy of all these particles is still greater than the energy of the coffee. Now, one of the things he's going to show us next is, and this is really a good point to think about the total, when you pour the coffee on the iceberg, would the iceberg change the temperature of the coffee, or would the coffee change the temperature of the iceberg?
The iceberg is at a lower temperature than the coffee. It contains more thermal energy because it is not at absolute zero, and its mass is much greater than the cup of coffee. Therefore, the answer to the question, which has more thermal energy, an iceberg or a cup of hot coffee, is the iceberg due to its mass. Now, let's consider this situation. If we pour the cup of hot coffee onto the iceberg, does the coffee warm up its area of contact with the iceberg, or does the iceberg cool off the hot coffee? To answer this question...
So, the iceberg is going to cool off because it has so many more particles, and so the iceberg, the amount of thermal energy absorbed by the iceberg and all these particles moving around is much greater than the cup of coffee. Okay, so You know, some of this should be a review from elementary school, the different states of matter. The first state of matter is a solid, okay? So we call these states or phases of matter, solid, liquid, or gas, and we're going to discuss plasma briefly. And the first state of matter we talk about is a solid, and we say that it has a definite shape and a definite volume. So, you know, if you think about something like your desk or your Chromebook, its shape doesn't change and the size of it does not change. So that's the basic definition of a solid. Now, this is the 8th grade, so we're not just going to stop there like you did in elementary school. We're really concerned with how the particles are moving and what's going on with the particles to cause this thing to be a solid or change into a liquid or gas. And the particles in a solid, we say, are tightly packed and they stay in fixed positions. So even though they're tightly packed, this diagram right here to the side, it shows the particles are connected with springs. And I kind of like this model because it allows us to think about these particles are really vibrating back and forth quickly, and they're moving around all over the place. Now, when it says they're in fixed positions, it means that this particle right here can't change positions with that particle up over there. So this one right here is not going to be able to change places with this one back here. They're vibrating back and forth and up and down. This particle is, you know, taking up this space and is vibrating all over the place, and so is this one. And it's vibrating back and forth, but it cannot leave. This one in the center can't switch places with the ones in the corner or the ones on the side. Now, a lot of times they'll show a model where it just has the particles like this, where they're all stacked in here. I don't like this as well because it doesn't really allow us to think about the particles moving. Okay, so even though they don't move position, they're still vibrating. Okay? The particles vibrate in place, and when we heat the particles, they move faster and faster until they start breaking these bonds. So you can think like, as we heated these particles up with this model here with these springs, and this one in the middle and the ones in the sides were vibrating faster and faster and faster and faster, and they were getting farther and farther away from each other because they had more and more and more and more and more energy. Eventually, these connections between them would start to break. Okay? So the atoms vibrate in place, and when heated, they're vibrating faster and faster until, as we said, eventually they begin to break those bonds. Okay, now I wanted to show you this little video right here because it does a good job of showing us how the particles are moving. So you see in this picture right here, these are the particles in a solid and they're vibrating back and forth. And in this one over here, in a liquid, they're moving around, but they're still connected. Okay, so there's still connections between the particles, and this is why in the next part we're going to learn that a liquid has a definite volume. But as you can see, the particles are constantly moving around. And finally, in this last picture, in a gas, the particles are completely disconnected from one another. And so we say that the particles in a gas are completely separate. And again, here it's showing that the particles in the liquid are moving around, and if you can imagine, as they move around faster and faster and faster, eventually they're going to break those connections that hold them together. They're going to become a liquid.